This is well, we say it's new. You guys have seen this before, and that's addition of Grignards to aldehydes or ketones, or this new thing called ethylene oxide. Where you've seen this isn't formally in lecture, but it is experiment 11B and C. So we've actually looked at this mechanism when we looked at our butyl bromide Grignard reacting with acetone. Is back where you've seen this. So we're going to spend probably the rest of the lecture talking about this particular reaction. So first, let's talk about Grignards and alkyl lithiums, which are kind of their cousin. Let's get a discussion on that out of the way. Then we can look at the actual reaction. So a Grignard reactant is this guy. It's an alkyl group that is bonded to MgX. An organolithium, very similar. It's an alkyl group and it's bonded to Li. Both of these function as, for all intents and purposes, an alkyl group with a minus charge. And so they're good nucleophiles, and they're also really good bases. Let's just write strong bases. If you remember back to the Grignard discussion, all the glassware to make that Grignard was dried in an oven for like a day ahead of time. And so you definitely want to avoid water or any other kind of protic hydrogen. You can't have any protic hydrogens on your molecule or as a solvent or anywhere around. So no alcohols, no NHs, no alcohols. You can't have an NH. You can't have an SH. Anything that can hydrogen bond is not going to work. Now we have a question here. Only elements you can use are magnesium and lithium. Yeah, that's right. When you're making the Grignard, you treat it with magnesium, and that's the only thing that can be used for that. And then the alkyl lithiums are just lithium. They have some other kind of, these are called organometallics, and they make some others, but they don't really serve the same purpose. If you want them to be a nucleophile, it's pretty much these two. Okay. Now, the alkyl or the R group, no, the halogen, can be a chlorine, a bromine, or an iodine. And you'll see them all used on paper, but typically the bromine tends to be the one that's the most common. So let's just put a box around that. Alkyl bromide is what you're most usually going to see. I've actually tried a Grignard with an alkyl chloride, and I didn't have much luck. The I don't even know if it really even worked for anybody. We ran out of butyl bromide for 11 BC, and we had to use butyl chloride. It was not a good thing. We didn't repeat it. And I can't remember if it just didn't work or the yields were bad or what, but I know I wasn't happy. So bromides are good, and you'll see iodides as well. I think just that alkyl halogen bond is just a little bit weaker, and so you're able to break it, displace it easier. Okay. Now, as far as the R group goes, these things are fantastic. You can make alkyl lithiums or Grignards out of like any R group at all. So I'm just going to show you some examples. You could have, like you guys did, you could have butyl bromide, where your R group's a butyl group. You could make it secondary. You could do it on the secondary. You could do that alkyl lithium or Grignard, right? They're interchangeable. You could put them on a cyclohexane ring, like that if you wanted to. You could put them on a benzene, right? That's like a benzene nucleophile. You could do it tertiary. So you could literally have this. The possibilities are endless. Those, they said vinyl too. You could even, if you had a double bond in there, you put a bromine on it, and then you could put this, you could make this an alkyl lithium. So it's like you can't find an R group where this won't work. It can just work with just about anything. But, well, when I said you can't find one where it won't work, that was kind of a lie. You can't do this. I couldn't have, um, let's do this. That wouldn't work, right? So that's kind of a big no. What's wrong with that one? Secondary. We said secondary is okay. Yeah, the OH is the problem. And the OH is protic, right? And so what would happen if you tried this? You have this OH sitting here and it will deprotonate. It'll get deprotonated by the Grignards and you will kill your Grignard because of that OH. We're going to learn tricks at the very last reaction we talk about next week, where we're going to do a protecting group. And you can get this to work, but you just have to do a little step ahead of time where you put a protecting group on the OH, do the Grignard, and then take your protecting group off. So it's not like you can't do it. You just can't do it like that. I have to hide it first. Okay, but that's for another day. Okay, so what we're going to do now is spend quite a bit of time looking at the reactions that these organometallic reagents can do. And we're going to talk about when they add to an aldehyde, what does it look like? When they add to a ketone, what does it look like? And then we're going to introduce ethylene oxide. Then we're going to practice looking at an alcohol and figuring out what pieces did it come from. So we're going to go backwards as well today. All right. So let's go ahead and I think we'll probably end up going to a second page in just a little bit, but we'll get there. Insert a blank page. So let's take a look at, see what kind of examples I want. Okay, here we go. I'm going to have them react with an aldehyde. So this will be number 1. Reaction with an aldehyde. This is going to give us, when you react with an aldehyde, it's going to give you a secondary alcohol. So if you have to make a secondary alcohol, then when you take it apart, you know that it's a Grignard or an alkylithium plus an aldehyde. So as you're going through your homework that you're going to have to do this weekend, secondary alcohols came from Grignards plus aldehydes. And when we start ripping them apart, remember that. So let's go ahead and let's do one. I'm going to take I'll just take an alkylithium and I'm going to have it react with, we use a 3-carbon aldehyde, nothing too crazy. I find it easiest with these to just do a little mechanism really fast. And I just draw, just so I don't make mistakes of who's hooked to what. This is really cyclohexane with a minus charge on it. That's what it really is. And it's a nucleophile. It's going to attack the carbon of the carbonyl because that's where the delta plus is. Talked about that in lab. Push electrons up. And I will get as my intermediate this guy. Here's my cyclohexane. Here's the carbon it just attacked. Has an H on it, has an O minus on it, and then has 2 carbons attached to it as well. And then you just do H plus. So you put it into like dilute sulfuric acid, and you have, there's your OH and the 2 carbons. This is a secondary alcohol. Okay, questions about that? All right. Let's do a reaction with a ketone. You'll see when we do that, that we're going to get a tertiary alcohol. So in your homework, when you have to rip them apart, when you see a tertiary alcohol, what you want to think is that it came from an alkylithium or a Grignard and a ketone. That's how you tear it apart. So let's do a Grignard this time. We'll do isopropyl Grignard. And the ketone that we'll treat it with, let's put it on a ring. Cyclohexanone. And again, I just run through the little mechanism. It's easy to do, and you won't make mistakes if you do this. Just in your head. So there's my ketone, and here's my nucleophile. It's just an isopropyl minus, right? And that minus charge, the carbon with the minus, will attack the carbonyl. Electrons go up on the O, and I will have this. My cyclohexane, it has an O minus on it from that former carbonyl. And then it has the carbon that attacked, which was the center of that isopropyl group. And then we have H3O plus. And all that's going to do is just protonate the alcohol. So here is our product. And you see that carbon bearing the alcohol has 3 R groups on it. The isopropyl, and then one side of the ring, and then the other side of the ring. So it is a tertiary alcohol. Okay, so far we can make a secondary alcohol and a tertiary alcohol. We haven't talked about making a primary. That's what we're going to do next. But before we do that, any questions on secondaries or tertiaries? All right, so the third type of reaction is going to be reaction with formaldehyde or ethylene oxide. And that, either of those, will give us a primary alcohol. So we'll tackle each of them separately and show you what the difference is and what ethylene oxide is. So let's first do the more familiar one, which is reaction with formaldehyde. Formaldehyde looks like this. It's an aldehyde, as you can tell by its name, right? But there's no alkyl group on it. It's just H's. So this is really a subset of reaction with an aldehyde. But because we don't have an R group in our product, we're missing an R group. So it's not secondary, it's primary. Ethylene oxide is an O that's part of a 3-membered ring. Looks like that. And sometimes it's called just epoxide. An epoxide is actually a class of compounds that are 3-membered rings with an O. This is the most common one. So if people say, oh, yeah, I treated it with epoxide, that's what they mean. That's like having a solvent, diethyl ether. Everyone says, oh, go grab that can of ether. Well, an ether is a functional group, but it's so common that diethyl ether, everyone knows that it's ether. But it's kind of the same thing as if you're going to use acetone, saying, oh, hey, go grab the can of ketone. No one says that, right? But it's kind of because it's so common, epoxide stuck, even though technically that's ethylene oxide. So let's do formaldehyde first, and we'll see how it gives you a primary alcohol. So let's do a tertiary alkylithium. Let's do this one. There's a tertiary alkylithium, and I'm going to treat formaldehyde with it. There's no mystery on this mechanism. It's the same as it was. This tertiary alkyl lithium is really just a tert butyl group with a minus. Effectively, that's what it's going to act like. It will attack the carbon. Electrons go up. No surprises so far. So we will have a C to an O minus H's. And then down here is my tert butyl group. And then when I protonate, this is what I have. I have a tert butyl and a CH2 and an OH. And this is a primary alcohol. I have just one R group on the carbon with the OH. My computer's trying to update Adobe. Hang on, I have to stop it. There. Did I go anywhere? I don't think I did. When you're making a primary alcohol and you use formaldehyde, what this will do that kind of makes it maybe easy to recognize when to use it is it adds one carbon to your alkylithium, to RMGX or RLI. It'll just add one carbon and make it a primary alcohol. Okay. Now let's look at ethylene oxide. Let's do, I don't know, let's do benzene. And we'll do MgBr. And I'm going to react it with this guy. Now that's something we haven't seen. But if you think about the characteristics of that epoxide group, the oxygen's electronegative. And so it's pulling electron density towards it, right? We've seen that a lot. That means that the carbon that it's attached to, so the carbon right there and the carbon on the other side, they're symmetric, right? That carbon has a delta plus. So when we're looking at where that Grignard wants to attack, it's not going to attack the oxygen, which has a delta minus, right? Those are basically two nucleophiles together. That's not going to happen. The Grignard is going to attack the carbon that has the delta plus. So let's redraw it because I just made it pretty messy here. So we effectively have a benzene with a minus charge, right? That's my Grignard. And I have this epoxide. The Grignard will attack at the carbon because that's where the delta plus is. And the three-membered rings are really strained. And something's got to give because we didn't draw them in there, but there are two H's here, right? And so I can't just attach it because it'd be a 5-bonded carbon. So it has to pop open. And the direction it will pop open is to give the electrons to the most electronegative thing. So it pops open like this and gives those electrons to the oxygen, which the oxygen's perfectly happy with because it's electronegative. So you end up with your benzene bonded to, let's keep track of it. I'm going to number these carbons, maybe make it easier on us. So we have 1 and 2, right? Carbons 1 and 2, and the O, easy to recognize it. So the benzene is bonded to carbon 1, and I broke the carbon-oxygen bond. So the oxygen's flipped out. It's attached to carbon 2. Carbon 1 is now just attached to carbon 2. That's all that's there. The oxygen's not there. And then we have O minus. So the oxygen ends up out at the end. And then when I protonate, looks like this. It'll be a CH2, a CH2, and an OH. Just like that. So it's primary. And notice that I added 2 carbons. So if I want to do a primary and add 1, formaldehyde. Primary and add 2, Grignard. All right, let's do some practicing. Okay, we're going to practice a couple forward, and then we're going to practice tearing a few of them apart. So I'm going to stick a page in here. All right, so let's see what you guys can do. Let's take this alkylithium and have you add it to this aldehyde. So we have that, and then we have H3O plus, and draw that product real fast. Okay. I'm just gonna, like I always do, just a little mini mechanism. You'll find mechanisms from here on out are your friend. So there's the minus charge, and it's going to attack the carbonyl. Electrons go up, and so it will look like, and you don't have to make it fancy. It'll look like this. A C, there's an H on it from the aldehyde. It has an OH on it after it gets protonated, and it is attached to that. That is literally as fancy as you need to get when you rewrite it. Okay, and notice it's an aldehyde, so we got a secondary alcohol. Any questions on that one? Okay, let's try another one. There's that one, and we will add it to, oh, let's do ketone. That'll test you. Okay, try to draw that product. Alrighty. So just redrawing this guy. I have a minus charge right there. That's where I'm going to be forming my bond. So this is going to look like this. And put an OH there. And then I come down, and that carbon, the carbon that I just attached has a dot on it, right? I'm going to do like that. It's got an ethyl on it and an isopropyl on it. Looks like someone running almost. There it is. Okay, notice it's a tertiary alcohol. Doing okay? Okay, let's do one more. Let's just take the same one and do epoxide. See if you can draw that. Okay, here we go. Um, oof. So I'm going to sketch it over here. So it's this minus guy, and it is going to be attacking the carbon and popping this open. So I will have to redraw my Grignard. It's the big part. Then I'm going to have a CH2 and a CH2 and an OH. So it added 2 carbons and it's a primary alcohol. There's a funny OChem joke. It's funny to me. I don't know if it'll be funny to you guys. It's funny. I've been doing this now for about 30 years. And when I originally we would tell this joke, it's kind of funny. And students would get it. But then 30 years went by and now people like look at me and they've never even heard of it anymore because this was a funny joke back before you guys were born, right? Have you ever heard, in order to appreciate it, have you ever heard of a song out of the 50s? And I was not alive in the 50s, so it was an old song for me even, that is Purple People Eater. You,
Yeah.
yeah, what one-eyed, one-horn, flying purple people eater, right? Nope, nope. Sounds kind of familiar. You could probably find some kind of YouTube thing about it. Okay, it's just this goofy song about a one-eyed, one-horned, flying purple people eater. And so the OChem thing with that, so it's not going to be as funny to you now, is this. Do you see how that relates to that? And keep in mind, this is an ether, and this is diethyl ether, right? Ethyl ether. Do you see how that figure? It's a children's song. I think it kind of is. This is a propyl people ether. It's kind of funny, but yeah, if you don't know the song, you're like, yeah, that's not funny at all. Oh my God. Yeah, right. It's like a dad joke, right? Okay, so let's practice taking them apart now. So here we go. What you're going to do now is go backwards. Here is your product. And I want you to go backwards and give me the Grignard or the alkyl lithium, I don't care which it is, plus whatever would give you that product. Okay, so the way you approach these is first look at that alcohol and classify it. Is it primary, secondary, or tertiary? That'll tell you what you're dealing with. So what are we dealing with? Yeah, it's a secondary. So we know that if it's a secondary, we know that it came from the Grignard or alkyl lithium plus an aldehyde. So at least I know kind of what I'm aiming for in terms of a functional group. Then what you do, there are a couple ways you can accomplish the task. Put a dot or a box or something on the carbon with the OH. Identify and lock down that carbon because that carbon, the one with the OH, it is that C double bond O carbon. It is not part of the Grignard. It is part of the aldehyde. That's one of the biggest mistakes is people include that carbon in their Grignard, but it couldn't be because the Grignard attacked it to make an OH. Then what you do is you cleave on either side of it. So step 2 is somehow box the carbon with the OH, and that carbon is your C double bond O. Then cleave on one side of it. That's going to tell you your two pieces. So what I'm going to do is cleave on this side. The half that has the carbon, the half with the box carbon or dotted or whatever, that's your aldehyde, right? And the
Oh,
half without that, that's your Grignard. So this thing, if I do where I put my little green line right here, this, if I break it apart like that, it's going to have come from this. The carbon with the dot is in this big piece. So it's C double bond OH. The part that left, which is this part right here, this half doesn't have the dot carbon. That has to be the Grignard.
yeah.
Just like that. Okay, everyone kind of get the idea? Okay, take this molecule and show me the other pieces it could have made. This is just one way to do it. Show me what else could have happened. So we'll go down this way. I want the other two pieces that potentially could have occurred. Okay, so doing it the other way, I just have to cut it on the other side. So I'd cut it like right there where that purple highlighted is. And then my OH piece is the other side, actually. It's going to be like this. And then the Grignard is this piece, or alkylithium, whichever. That's the other option. That would give me the same product. Okay, let's do one more. What if we did this? Put this guy right here and give me an option for taking it apart. No, it doesn't matter which side you cleave. The question was, does it matter which way I choose? And on paper, certainly not. Sometimes it is easier if you're told, okay, make this, and you can only use pieces 4 carbons or less, which is what we tend to do to you. If that's the case, if we say you can't start with anything 4 carbons or less, I'd probably want the second option because both of these pieces have 4 carbons. I wouldn't have to build them very much. This one has 5, so I'd have to somehow make that and then use it. But just on paper, it doesn't matter. For the homework you guys have due on, I don't know, when is it due? I'll figure it out. As you're working, you can do any way that you want to. Okay, so on this one, let's identify the carbon that has the OH. That is always going to be my carbonyl carbon. And then I'm just going to break, I have 3 different things I could break off, right? I'll break off, I don't know, the ethyl group. Let's say I decide to break right there. So this would be ethyl lithium or ethyl Grignard plus that big old piece has the double bond O. So it would look like that. Okay. You could have done the isopropyl group. If I broke that off, it'd look like this. I'd have the isopropyl as a Grignard. And then if I did that, this piece has the OH on it, so it would look like this. Be the benzene going to the C, and then the ethyl came up, it looked like that. Or I could have broken the benzene off, in which case it becomes the attacker, the alkyl lithium, and then my ketone looks like this. So any one of those would be okay. And the way you choose is just which, given the parameters of what you're trying to do, which one's the best one, which is the easiest. Yep, so we had finished up Grignards and talked all about them and alkyl lithiums as well. So the next place, and this is still under, just to get ourselves oriented, this is still synthesis of alcohols. And this is just continued. All right, so we did a review of alcohols from double bonds, which you guys all know about that. That's a review of Unit 4 stuff, basically. Talked about Grignards, did a bunch of examples of those. And now we're going to look at taking carbonyl compounds and reducing them, and there are a few ways to do that. Before I launch into it, I see a question. The lab practical, is it graded automatically? You know, it's a combination. It is set up to, I think every question grades automatically, kind of loosely in quotes, but some of it you guys fill in, you have to write things. And if Canvas doesn't, if it's not exactly what the pre-programmed answer is, it tends to mark it wrong, or sometimes it won't mark it at all. And so you'll get it'll grade automatically, but it's not like the real grade. What I do is I go through and I actually look at each one you got wrong. And if it's just a misspelling or something, or you're close, I give it to you. Sometimes, let's say the answer is, I don't know, there's some number, it's 78, say it's a boiling point, 78. And you happen to write down 81, but it was 78 plus or minus 2. So 80 would have been okay, but you write 81. I'll go back and if it's reasonable, give those to you. So you won't get your actual grade till I've gone back and made sure that the computer program hasn't done evil things to you. I want to fix that. Okay. All righty. Oh, and by the way, your exam, the graded exam, that'll be visible to you early evening, I think is when I can put it up. All right, so you can look for that sometimes 6-ish, 7-ish, thereabouts, I think. All right, any other questions? Okie dokie. So we're going to look at reduction of carbonyls. You can reduce ketones and aldehydes, which this slide's specific to. You can also do carboxylic acids, esters, amides, basically any carbonyl compound. And most of that we'll save for 421. You actually have a whole chapter on esters and amides and acid chlorides and carboxylic acids, all that. We're just going to focus on aldehydes, ketones, and basically touch carboxylic acids and esters very lightly because you can turn those into alcohols too. So first thing, if you have an aldehyde or a ketone, you can actually reduce it, and it acts just like a C double bond C in that you can use hydrogen and a metal catalyst. What's typically used is Raney nickel. And as far as what Raney nickel is, it's, I'll write it over here. Again, to try to make room. Raney nickel is just a finely powdered, so it's a finely powdered nickel metal that's saturated with hydrogen atoms. And so if you treat a carbonyl with hydrogen, Raney nickel, and oftentimes you'll see pressure and heat, especially with the other catalysts, which aren't quite as good for doing carbonyls, you'll see pressure and heat. You can get that ketone or aldehyde to turn into an alcohol. And we'll go ahead and look at the mechanism and then do two examples. And you'll see we'll do an aldehyde
and we'll do a ketone. And you'll see that if you have an aldehyde, it will turn into a primary alcohol. And then we'll do an example of a ketone, which has two R groups. That'll give you an alcohol with two R groups, which is, of course, a secondary alcohol. Now, as far as the mechanism goes, it's a pretty straightforward mechanism. You have your C double bond O, and then you have, let's just do an aldehyde, just a generic one, right? R group right there. And then you have your Raney nickel. So here's your metal, nickel. And the nickel has hydrogen atoms embedded in it. And just like we saw with when we were doing double bonds and triple bonds, the one hydrogen can go to the carbon and one hydrogen can go to the alcohol. And it's a syn addition. So it's analogous exactly to an alkene. And what you'll have is you'll have a C, an O. The C has an H, the O has an H, and then you have the H from the aldehyde and your R group. And so you can see that it turned into a primary alcohol. Okay, so some of the things you have to be careful of are these are the same conditions that will reduce double bonds and triple bonds as well. So you need to be mindful that if you do this, you'll also reduce any C double bond C or C triple bond C in the molecule as well. So let's go ahead and let's do a couple of real examples so that you can see how it actually works. Let's do something called benzaldehyde, which is an aldehyde on a benzene ring. And we'll do H2, Raney nickel. And a benzene ring has double bonds in it, right? Let me redraw this without the circle. Go old school with it like that. Benzene rings, though, they're their own thing. They're not a normal alkene. They're highly resonance stabilized. And so you can just make a note that these double bonds are unreactive. This benzene ring, it won't reduce under these normal conditions. There are specialized, rather harsh conditions to reduce those double bonds. Under just H2 Raney nickel, nothing's going to happen to it. And so what you'll get from this is your benzene will stay intact, and you'll have the carbon with the oxygen. The oxygen will pick up an H, the carbon will pick up an H, and you have a primary alcohol. Let's do a ketone. What if I did this ketone? And let's put a double bond in there just for fun. And we'll do H2, Raney nickel. What'll happen there is your oxygen will pick up an H, your carbon will pick up an H, and so will that double bond, right? So this will also pick up H's. And you'll have, when you write that thing without all the H's, which is kind of cluttered, right? When you write it, it becomes that. And you can see that that is a secondary alcohol. Okay. If you used H2 and platinum, would it affect the C double bond O? You could do that, but that's where you would need pressure and heat. The catalyst just isn't as reactive as Raney nickel. So if you were to, you will see H2, platinum, or palladium, but often you'll see an elevated temperature and elevated pressure, like 5 atmospheres, 80 degrees, that kind of thing. But yeah, it would still affect the C double bond O. Now, let's say you want to do a reduction, and like for the second one we did with the ketone, I want to get the carbonyl to an OH, but I don't want to mess with the double bond, right? Which is a very common thing to want to do. This isn't a good way to do that, but there is another reduction method, and that's a hydride reduction, and that's what we'll be looking at next. So All right, so B, both of these fall under an umbrella hydride reduction label. And hydride reduction uses H minus to perform the reduction. It's going to use H minus as a nucleophile. There are two different hydrides that are very commonly used. One of them is called sodium borohydride, NaBH4. Now, you guys have been introduced to this one before when we did oxymercuration, right? We did HgOAC2 with water, right, on a double bond. And then to get that mercury off, we did step 2, NaBH4, sodium borohydride. So that's a very common reagent. It's a little bit limited though. Make a note here that it is for aldehydes and ketones only. Aldehydes, ketones only. It's a little bit milder, and because it's not as reactive, it doesn't do as much stuff. If you want something with a little more juice behind it that will reduce more things, reduce things a little quicker, you could do lithium aluminum hydride, which is LiAlH4. It's more reactive and it reduces all carbonyls. So let's just kind of summarize some things over here. We have NaBH4, and it will do ketones and aldehydes. The advantage of it is that it is easy to use, and you can use protic solvents. A lot of times you'll use an alcohol as a solvent. And so this is the one you guys are going to do an experiment next semester where you reduce a ketone to an OH, and you're going to use sodium borohydride. You take it to the balances, you open the container in the room, scoop it out with a scoopula. We do it in methanol. Really easy to handle. It's no more different than handling, I don't know, salt, right? Lithium aluminum hydride's a different deal. It's more reactive. And because it's more reactive, it will do a whole list of things: ketones, aldehydes, carboxylic acids, esters, amides, acid chlorides, so acid halides. It will do C triple bond N. It does a lot of things. And so it's much more generic and more useful, but it's hard to use. Because it's so reactive, you have to use it, you can't use it in an open room. It has to be used in an inert environment. So you have to use it in a closed system, a little box that has a bunch of like argon gas in it. And you also have to use aprotic solvents. And if you're not careful, it can cause fires. And so lithium aluminum hydride, we don't use it in lab just because it's just not practical in our environment to have something that is so finicky that you have to be so careful of. But it's a more all-around reducing agent. For just ketones and aldehydes, NaBH4 is preferred. You can use either on paper. You can use either one, right? What do you care? But if you're in a lab, man, I wouldn't use lithium aluminum hydride for a ketone or an aldehyde. It just technically, it is so much more difficult. It's just a pain in the rear. So, all right. Okay, now the mechanism for the reduction on those is the same. I'll just run through. We have the same kind of result. An aldehyde is going to go to a primary alcohol. A ketone is going to go to a secondary alcohol. We're going to take a look at, in the next couple slides, we're going to look at carboxylic acids and esters too, because they actually turn into alcohols. We'll look at those separately. But we'll do a mechanism with a ketone or an aldehyde, and then just a couple of examples. One thing that you don't have to worry about, make a note of this, we'll do it in red. Neither one of them will reduce alkenes or alkynes. They won't reduce C double bond C or C triple bond C. All right, so let's go ahead and do a mechanism. It's a pretty straightforward mechanism, actually. They act almost Grignard like the hydrides. So let's say you had a ketone, and let's just do one on a 6-membered ring, not a benzene, which is a cyclohexanone. The carbon of the carbonyl has a delta plus. So that carbon right there has a delta plus. It's attached to an electronegative oxygen. And so both of these reagents are a source of H minus. So the hydride ion, H minus, attacks the carbonyl, just like a Grignard would. Electrons are pushed up onto the oxygen, and you end up with your O. Now the O has a minus charge because it got that electron pair, and there's an H now attached there. And we have to protonate that O minus somehow. If you are in sodium borohydride, if you're using NaBH4, it is in typically an alcohol solvent. So let's say methanol is the solvent that we use. And so what'll happen there is that it will just grab the hydrogen from the solvent and you'll have your alcohol. So you would have an OH and an H, and that H right there came from the solvent. Basically, it's an H plus, right? It's from the solvent. Now, if you are in lithium aluminum hydride, so let's say you're going this way, LAH is lithium aluminum hydride because no one wants to write that over and over. This is in ether. And so there is no hydrogen on the solvent. We have no protic solvent with that. And so what you have to then do is you'll have to add H3O plus. And the H3O plus is the source of the hydrogen for the alcohol. So OH, H, and that hydrogen is from H3O plus. So the second workup step is a little bit different for each one. Okay, let's go ahead and just do a couple of examples with these guys. Let's do an aldehyde. And we can do step 1, LAH, step 2, H3O plus, and it will take that aldehyde and it will add a hydrogen to the carbon and then a hydrogen to the oxygen, and you get a primary alcohol. If you have a ketone, we'll do like that. Let's put a double bond in it, just like we did last time. And let's do sodium borohydride. We'll do sodium borohydride and ethanol. And here, your ketone will turn into an alcohol. Your double bond will stay put because the hydride won't reduce the double bond. And you end up with a secondary alcohol. And the double bond is left alone. Okay, any questions on this one? Okay, now, if you treat carboxylic acids or esters with, they require lithium aluminum hydride. They're reluctant reactors. So you have to use a more powerful reducing agent. But you can take carboxylic acids and esters and you can turn them both into primary alcohols. And we're going to just briefly look at that mechanism, not completely, but briefly. And I'll just show you just enough so you understand what's going on. You're going to study it in much more detail in 421. It's actually probably about 8 steps, and we're not going to do all 8 steps. It's not important for us at this point. But what's going to happen, and let's do a carboxylic acid just in general. In the mechanism, you have
your carboxylic acid, and hydride attacks the carbonyl, just like you are kind of used to. Electrons come up, they come down, and then they end up kicking out OH as a leaving group, which, we said does not happen very well. That's why this takes a really reactive hydride source to get this to happen, because you've got a terrible leaving group, right? And you're forcing it to leave. So that this particular step, it's actually a couple steps, they're not great, but you can get them to happen if your reactants are reactive enough. Then what happens, though, is you don't have an alcohol. You take a look at what I did. Hydride attacked, so I do have an H there. Electrons went up on the oxygen. Then they came back down and kicked out this terrible leaving group. This is what I've got. Check that out. What you have is an aldehyde as your intermediate on this. And I'm going to write it a little more normal here. We'll go like that. You have an aldehyde, but you're in hydride, right? And this thing reacts again. It reacts with more lithium aluminum hydride. And what you then get is you'll have H minus attack the aldehyde. Electrons go up. There's no coming down and kicking out a hydrogen. A hydrogen is not going to leave flat out, just won't. And once you're done with your H3O plus step, you'll have this. Electrons came up, stuck up, got an H on them, and you have that. So you can see you have a primary alcohol. That's basically what's called a hydrolysis mechanism, or a reduction mechanism, rather. Okay, so what you guys need to remember is what's going to happen when you're looking at either an ester or carboxylic acid. Let's just do some what they call lasso chemistry. Take the carbonyl part of the molecule, like that. That part is going to become the alcohol. Then the part that's remaining, let's do it in blue. This part right here, it just comes off protonated. So it leaves and it gets protonated. Okay, we'll do a few examples so you can see it in action. The aldehyde's just an intermediate. Their aldehydes are so reactive with LAH that you cannot isolate them. Now that being said, there are compounds that will stop at the aldehyde stage, but this isn't one of them, and you'll learn about them later on. There's one called dibol, diisobutyl aluminum hydride, and they're kind of permutations of hydride agents, and they'll stop at the aldehyde, but LAH will not. You can't isolate it. There's a shorthand, by the way, for not being able to isolate something. You'll see the intermediate in brackets. And what that means is that it's basically a pass-through. Okay, so we can put that in brackets. So let's do some real ones and see if you can predict the products. So let's do a carboxylic acid. And I'll treat it with LAH and then H3O plus. Okay, and then we'll do another one. We'll do 3 different ones. This one's a combination of 2 things. It's a ketone and an ester. And we'll treat it with LAH. Actually, we'll do 4. This will be even more fun. And then let's do that same. Let's do the same ketone and the ester. But I'm going to treat it with sodium borohydride and methanol. And we'll see if we can predict what's going to happen there. So here we go. When you're dealing with carboxylic acid or an ester, here's what you do. Just take and draw a squiggly line separating the acid part, or like the ester part, from the carbonyl. That'll tell you how it breaks. And then the C double bond O part, which is this part right here, you're going to turn that into an alcohol. Okay, so this will become an alcohol. So what you'll get on this first one is my alkyl group. That carbon that was the C double bond O has an OH, and I'm just going to put two H's on there to complete the octet. It becomes a primary alcohol. The other half leaves and gets protonated, so that's going to make water. Okay, and the water came from this part right here. It's a little bit thick. Came from this right here, protonated. Okay, see what you come up with the next one down. This one right here. Try that one. Okay, so we have our six-membered ring. Before we tackle the ester, let's tackle that ketone. What's going to happen to the ketone under the conditions of LAH? What's it going to do? It's going to become secondary alcohol, exactly. So that ketone reduces to an OH. The ester, I'm going to cleave the ester part off. So this part's going to leave, right? This section right here is gone. And the C double bond O is going to become a CH2OH. And then the OCH3 part leaves and gets protonated, CH3OH. So I actually reduced two things, a ketone and an ester in that. All right, then we switched reducing agents, right? I'm not doing LAH, I've got an ester, but I'm doing a ketone and an ester. The ketone will react with sodium borohydride, right? We saw that in the last slide. Ketones become secondary alcohols. What's the ester going to do with NaBH4? No one's willing to risk it. It's going to do nothing. And so it will just be C double bond O, OCH3. With this guy right here, there's no reaction with NaBH4. So it just sits there. Sodium borohydride's not strong enough to do it. So you actually can kind of tailor with your reducing agent which one you want. And there's a question, the OH on the ring, it will produce enantiomers, that's right, because the carbonyl is planar. So the hydride could attack from the front or the back. And so you would get a mixture of enantiomers at that carbon. It could be half R, half S. All right, try this one then, our last one. This will be a fun one. Let's do this. It's an ester in a ring, and see if you can figure out what that is going to look like. So step one, LAH, step two, H3O plus. Try your hand at that. It's a little intimidating looking, but use the same process we did. Draw a squiggly line at the carbonyl and see what happens. Okay, so we will break right there. And I'm not going to do anything fancy. I literally am going to redraw it just like this with that that bond that was right there broken. So I'm going to erase it. That bond's gone.
the carbonyl, the C double bond O, turned into an OH. And the thing that got kicked out, which is the alcohol group, basically, right, got protonated. Bam, there it is. So you ended up getting two alcohols like we did before with an ester, only now they're hooked together because they were in a ring with each other. Okay, and just for your notes, we probably should so that you don't look at it and think that we have um, a carbon that doesn't have an octet. There are two H's on that. What was the carbonyl? All right. And the next slide has a nice summary table for you that you might want to keep handy as you go through and do homework and things about the different reducing agents that we have encountered so far and what they'll react with. So for example, H2 and rainy nickel. Say you wanted to know what will it do? It will do alkenes, it'll do alkynes, it'll do aldehydes and ketones. It won't do carboxylic acids and esters. So this just gives you an idea of if you wanted to reduce certain things, which one would you choose? You can look at this table, figure that out. Any questions about the reducing agents? Okay. That takes us through then the synthesis of alcohols. You guys know them all. Pretty much they fall into, let's sort of summarize three main ways. To make alcohols. You can do them from alkenes, right, from a C double bond C. You can do a Grignard or an alkylolithium plus a ketone or an aldehyde or an epoxide, right? That's another way to do alcohols. And then the third thing that we just saw is from reduction with NABH4 or LAH, and that applies to ketones, aldehydes, carb acids, or esters. Okay, so those are really the things you see probably 99% of the time when you're making an alcohol. All right, now let's see what alcohols can do. One of the most useful things that an alcohol can do, wow, this slide is just a wall of information, so we'll break it down slowly, is they can be oxidized. That's the whole crux of this slide, is oxidation of alcohols. Now, we saw the opposite process. We just did reduction of a ketone to get to an alcohol. Well, if you have an alcohol and you oxidize it, that's the opposite process, you'll go to a ketone. So we just did this, right? We can add H minus, and this is reduction. Ketone goes to an alcohol. Now we're going to learn to go back doing an oxidation. So what you're going to see is that primary alcohols can be oxidized, and they can make, if you have a primary, it can go to an aldehyde, right? And oxidation is basically taking hydrogens away. So I remove that one and that one, go to an aldehyde. And then if I oxidize it further, I can take that hydrogen away and go even further, and I can go to a carboxylic acid. So primaries, you have a couple options. You can either stop at an aldehyde or go to a carboxylic acid, and we'll teach you the reagents for each one. And then if you have a secondary alcohol, you're a little more limited. Secondary alcohols are pretty much just going to go to ketones. There's no kind of intermediate thing that you can stop at. Tertiary alcohols were my favorite because when you're oxidizing, you have to remove a hydrogen, right? I'm getting rid of this hydrogen and that hydrogen to make a ketone.
Well, tertiary alcohols in this area here, there's no hydrogen to remove. So if I can't get rid of an atom there, I can't form a C double bond O or I'll violate the octet rule, right? So tertiary alcohols were phenomenal because they were no reaction. So they were my favorite because I didn't have to learn anything about them. We're not going to see that happen. All right. So just to sort of summarize it up before we get into the reagents, if you have a primary, you can go to an aldehyde. That's like your first stop. And then if you go further, that aldehyde can go to a carboxylic acid. If you have a secondary alcohol and you oxidize it, it will give you a ketone. Okay, there's nothing else. Yeah, I like that. Yeah, me too. I always like things that were no reaction. I was like, I can handle that. So, all right. Okay, now it's listing some reagents here. This is all these things, these notes are just the reagents. Typically, the reagents that are used are some form of chromium. So let's go down here and let's look at the notes here. Note number one. One of the reagents that's used is chromic acid. And there are several ways of getting chromic acid. You can use either CrO3H2SO4. So that's one set of reagents, CrO3H2SO4. Or another set is sodium dichromate, which is Na2Cr2O7H2SO4. These are two different oxidizing agents. And they're very common use. They're actually they're heavy metals, and so they're toxic and they're difficult to dispose of, but they're really good oxidizing agents. They both effectively form H2CrO4 when the reagents are added together. You can see the sulfuric acid is making the chromic acid. When they do their reaction, which we're not going to worry about the mechanism, you're not responsible for that. But when they do it, the chromium is going from a +6 down to a +3. And in both cases, whether you're using chromium trioxide or sodium dichromate, it's +6 going to +3. So the chromium's gaining electrons and it's being reduced. And you can actually follow that by color. The color turns from an orange when it's +6 to kind of a greenish blue when it's +3. So you can theoretically, you can tell when your reaction's done because it starts out orange, turns blue, which is kind of cool. I actually investigated this, and when I was doing research as for my PhD, I never used these. My compound didn't need them. But I was going to do a lab for 420. So we were fooling around with a chromium reduction or chromium oxidation because it's so common. And we set it up thinking, oh, it'd be so cool to go orange to blue. This will be great. And it stayed kind of a pea soup green the whole time. So we didn't do it. We're like, oh, that was boring. But in theory, it goes orange to blue. In reality, it seems to be pea soup green at all times. Okay, so that's those two. Sometimes the chromium trioxide is called Jones reagent. So you may see this referred to as Jones reagent, sort of like Lindlar's catalyst. Jones reagent is just a named reactant. Okay, so we have those two. And then there's another reactant that is commonly used, and we'll just call this number 2, and that's called PCC. PCC is short for pyridinium chlorochromate. You can see the PCC, pyridinium chlorochromate. And what it looks like is this. It has a pyridine molecule. Pyridine's a benzene with a nitrogen in it. Looks like that. And pyridinium, it's been protonated, so it's NH with a plus charge. And then the other part, the chlorochromate part, is this Cl CrO3 minus pyridinium chlorochromate, and that's equal to PCC. And typically its solvent is methylene chloride. So the CH2Cl2, nothing special, it's just a solvent. All right. So that's a third reactant. And then some other common ones that you might see is potassium permanganate. That's an oxidizing agent. Nitric acid, that could be used, not that common. Bleach can also be used. Okay. So got a whole lot of possibilities. And what we're going to do is take a look at when you would use one versus another. There's only really one specialized one in there, and that's PCC. PCC is the only one in this whole list that will take a primary and will stop at an aldehyde. So PCC will take a primary alcohol and it will stop at the aldehyde. All the others will go all the way to a carboxylic acid. All right, so what we're going to do is kind of formalize that, and then we'll use some of these in different sort of examples. So up here, you guys have some, it says 1, 2, and 1. Let's change that. It should be 1, 2, and 3 right there. Okay. So the first thing, this is the important thing of what all these guys are going to do. PCC will form aldehydes. Chromic acid, any of the chromic acid ones will form carboxylic acids from primary alcohol. So all these others will form a carboxylic acid. And then if you have a secondary alcohol, it doesn't matter what you're using, PCC or chromic acid will form ketones. All right, so let's go down here and let's make a list. If you have a primary alcohol, it will go to a carboxylic acid. So this is complete oxidation. And it will do it with CrO3 H2SO4. It will do it with sodium dichromate, Na2Cr2O7 H2SO4. It will do it with KMNO4. It will do it with bleach. And it will do it with nitric acid. Just about every oxidizing agent will take the alcohol to a carboxylic acid. Aldehydes are very hard to stop at. If you wanted to stop at the aldehyde, you have one way of doing it, and that is only of the ones we've given you, only PCC. PCC only. None of the others will do that. The problem with aldehydes is they oxidize really easily, and those others are just way too reactive. All right. So let's go like this so that you have them all grouped together. Okay, now secondaries are great. I loved secondary alcohols. They go to a ketone. And this is with every oxidizing agent. Even PCC, every single one of them. Super easy to remember. All right, so let's do some practice. Show you guys how it works. Let's do an alcohol involving a benzene ring, like that. And let's hit this with sodium dichromate. Okay, write down what you think the product is. Hopefully, this is what you got. It's a secondary alcohol. Easy as that. Goes to a ketone. Let's try this guy. Here's an alcohol, and we'll treat it with KMNO4. Write down that product. And I'll give you another one. Okay, I'll just write them all down, and then we'll go through them. Okay, that should give you enough. I'll give you guys a minute to catch up writing those down. I can see I have a space problem. I'm going to space things out a little bit while you write them down. There. Okay, I think I have enough room to write things now. All righty. So we'll just go down. So the next one we'll do is just this unbranched kind of boring alcohol, butanol with KMNO4. It's a primary alcohol. And so it's going to make carboxylic acid unless I use PCC. So hopefully you got this, carboxylic acid. The next one's also primary alcohol, the cyclohexane with the OH next to it. And with PCC, I can make an aldehyde. So that one should have got an aldehyde out of that. And it looks like there it goes. Looks like I have a lag. I may have to fix that. We'll see. Okay, questions on those three down that one column? We're okay? Good. Okay, then let's go to the one I was moving all around to give myself space. That's the top one in the next column, this guy here. I'm doing two different things to it. It has two alcohols in it, and I'm going to treat it with PCC in one case and then chromium trioxide sulfuric acid in the other. PCC will take primaries to aldehydes, secondaries to ketones. And I don't have any primaries in there, so let's just redraw my carbon skeleton. There's that. What's going to happen to my first alcohol? The one that's at that branch, so the one that is right here. What's going to happen to that? Yeah, nothing. Exactly. It's tertiary, so nothing happens. It can't get oxidized. It stays as an OH. And the other one, a ketone. Okay. What if I used the chromium trioxide, so the bottom option there? What's going to happen there? What will it look like? it would actually be the same thing. Exactly. Yep, no difference. Tertiary, nothing happens. Secondary goes to a ketone. Okay, so no difference. You could use either one in that case, and that'd be fine. PCC is a little more expensive, so typically you don't use it unless you have to. It's kind of specialized. You use it in a real life situation for primary to an aldehyde. You wouldn't just use it to do any garden variety oxidation. That something else could easily do. Okay, but on paper, we're all millionaires, and so you could use PCC if you wanted to. It'd be fine. In real life, you'd probably get slapped in the head by your research director for using PCC here. It's a waste of money. Okay. Now the next case is where a case where you would want to use it, right? So go ahead and see if you can predict what those are going to look like. 3 OHs. I'll do the PCC version first. The secondary went to a ketone. The OH out on that ethyl group, it's a primary. So with PCC, it went to an aldehyde. And that tertiary, nothing. Stayed an alcohol. Now, if you do the chromium trioxide version, I'm actually, because I'm going to run out of space, I'm going to write it over there. Well, the secondary, secondary always goes to a ketone. Tertiary, never anything happens, right? So it stays. What's going to happen out on this ethyl group, though? What's that primary going to become? Carboxylic acid, exactly. There we go. There's a carb acid.